So today we're going to be talking about how an action potential takes place along a neuron. And here we can see the action potential graph. Now there's a lot to really understand about this graph, and I want to give you all the tools that you need to really understand it rather than just memorizing these little parts. We need to be comfortable with the anatomy of a neuron, graded potentials versus action potentials, as well as ion concentration and movement of sodium and potassium. So I'm going to go through those three things to help you understand this graph. On the y-axis, we have membrane potential, the millivoltage of the cell. And as you can see at rest, indicated by this dotted black line, we are at negative 70 millivolts. Now, we always want to be at negative 70 millivolts for these neurons at rest. This is really important for the life of the cell so that we can continuously have this exchange and movement of ions across the membrane. We're going to talk about why we're at negative 70. We need to look at how sodium and potassium move across the cell membrane. There are three different ways that sodium and potassium can move across the membrane. And it's important to know the difference between these because a lot of students get them mixed up or assume that it's all really the same. So we have our cell, it's more negatively charged. Potassium is highest inside the cell, always highest inside the cell. Whereas sodium is highest outside of the cell in concentration. So the first two types of transport are passive. Passive transport means that these ions are going down their concentration gradient. And what that means is they're going from an area of high concentration to an area of low concentration. So like for sodium, highest outside the cell, lowest inside, it's going to flow into the cell. It's like going from high to low to hopefully balance it out a little bit. So sodium is going to passively diffuse into the cell, whereas potassium passively diffuses out of the cell. Now there are two different types of passive transport. Firstly, we have leaky channels. These channels are always open. They never close. They are always open. They are leaky. So potassium going out, sodium going in because of the high to low passive transport. Secondly, we have another type of passive transport, but now they're gated. So they're not always open. So potassium going from high to low, so still going the same direction, but now we have a little gate on it. And sodium going into the cell. And we have that little gate here. So what that means is a ligand, such as a neurotransmitter or hormone, has to click on and bind to this channel or receptor to cause the gate to open. There's a trigger. It's like a lock and a key. This ligand, neurotransmitter or hormone, is like the key and the gate is the lock. So certain scenarios are going to open these gates. This is what we're really looking at with the action potential, right? In the action potential graph, everything's shifting and it's due to the changes in these gated channels. But the last type of transport is active transport. And active transport means we're going against the concentration gradient. So we're going from an area of low concentration to an area of high concentration. So essentially we're making this difference even greater. We're going against the gradient. So we're going from an area of low to an area of high. So our sodium is going to be leaving the cell and potassium is going in. So we're flipping the direction here for active transport. So again, with the millivolts of negative 70 being our resting, all three of these are going to be playing a role. However, with our changes in millivoltage with the action potential, it's really due to the fact that these gated channels are opening and closing. But you may be asking, Caitlin, how is our resting membrane potential negative 70 when we have a positive ion coming in and a positive going out? Doesn't that equal zero? No, because this cell membrane is significantly, about 50 to 100 times more permeable to potassium, which basically what that means is we're gonna have a whole lot more of these potassium leaky channels than we do the sodium ones. So we have more positive ions leaving the cell, making it more negative. So that's what's causing our negatively charged cell. The potassium ions are leaving more than the sodium are coming in. Baseline resting membrane potential is negative 70 millivolts. Then we have some sort of stimulus that's applied right here. And as you can tell, that is causing that cell membrane to become more positively charged, as we can see here. This is low. Where is this happening on the neuron? Well, it's happening on the dendrites and the cell body. So some sort of ligand, such as a neurotransmitter or hormone, will bind to these receptors on dendrites. That's going to cause the opening of sodium channels. Well, when sodium channels open, these gated channels open for sodium, comes in the cell, that cell is becoming more positively charged because we have more positive ions coming in, so we're going to become more positively charged due to that sodium coming into the cell. So closer to that negative 50 threshold, which is this red dotted line is the threshold. So this here is the graded potential. Stimulus is applied, sodium flows into the cell. Now, depending on how strong that stimulus is going to determine how much sodium comes in the cell. If there's a lot of sodium that comes into the cell, we're going to probably reach that negative 50 threshold. However, if that stimulus is really small, it's weak, then this graded potential may just do this, loop. It doesn't reach that threshold. So then this action potential doesn't take place. So that stimulus has to be strong enough to cause that millivoltage to get up to negative 50 in order for an action potential to occur. Sometimes a graded potential could also just cause the membrane to become, or cell to become more negative. That's possible as well. Obviously, no action potential will occur there either. Stimulus is strong enough to cause that graded potential to reach that negative 50 threshold. Some sources say negative 55 millivolts. If it reaches this negative 50 threshold, this entire action potential will happen. There's no stopping it. This is called the all or none principle. Once this action potential starts, it will finish. So what happens here? We reach negative 50, and as we can tell, we go from that negative 50 up to about positive 30. So our cell is becoming more positively charged. This is where the ions come into play. Again, we are looking at these gated channels. Which channel is open when we become more positively charged? You should think the sodium. Sodium gated channels are going to open. Sodium positively charged come into the cell, making the cell more positively charged. So our sodium channels are open here. And this is called depolarization. When the cell becomes more positively charged, it's depolarizing. Once we reach about positive 30, we can see a turning point. Now we're becoming more negatively charged. So what gated channel is open here? It's got to be potassium. We have a positively charged ion leaving the cell. Taking positive away means we're becoming more negatively charged. So our sodium channels close and our potassium channels open. When we become more negatively charged here, this is called repolarization. Becoming more negatively charged here. Potassium channels stay open here, and it actually crosses that threshold negative 50 and that resting membrane potential, and it overshoots here. Once it goes past that resting membrane potential of negative 70, this is now called hyperpolarization. We've gone past that resting membrane potential. This is hyperpolarization. And at this point, we have our potassium channels still open. However, sodium channels are still closed here, even though I'm about to write open. However, at about right here is when the potassium channels close, so they're both closed, going back to resting membrane potential. Just applying it onto the neuron here, what's happening? Dendrites, cell body is where the graded potential is occurring. Once it passes this axon hillock, we have that full action potential occurring. And that action potential will reach the synaptic terminals here of the neuron. And if it's communicating with another neuron, it's going to communicate with the dendrites of the next neuron. Great drawing there. And it's going to cause this whole process to happen again. So these neurotransmitters that are released in the neuron synaptic terminal are going to communicate with the dendrites of the next neuron, causing this whole process to happen again. So this is how two neurons are really communicating with one another, through graded and action potentials. So now I want to tie all of this into the actual anatomy of a neuron and where all of this is taking place. So remember back, the graded potential is what occurs first to hopefully reach that threshold and cause the action potential. Well, where does that happen? The graded potential occurs on the dendrites of the neuron and goes into the cell body as well. So as you can see here, there is some sort of ligand that has binded itself to the channels, the receptor, the channels for sodium to flow into the dendrite. So this ligand binds, sodium flows into the dendrite, and that's going to cause this cell to become more positively charged. So we're depolarizing the cell. Remember back to that graded potential, which when it leads to an action potential, it's going to cause the depolarization of a cell, causing it to become more positively charged. If that stimulus is strong enough, it's going to reach that axon hillock, and the action potential is going to carry along the axon of the neuron and down to the axon terminals. And as you can see, when this action potential reaches the end, it's going to cause the opening of those calcium channels. Calcium channels are going to open, and what that's going to do is it's going to trigger the release of these neurotransmitters, which are just waiting in the synaptic bulb so patiently, which are indicated by these purple little dots. So these neurotransmitters are going to be released from the bulb, which is here. So these neurotransmitters are released from the bulb into this synaptic cleft, the space between the bulb and the next cell, in this case another neuron. So these neurotransmitters leave the bulb and they drift towards those sodium channels, those receptors on the next neuron, on the dendrites. So as you can see, these neurotransmitters bind to those receptors, the purple dots here. That's going to open up those sodium gates, allowing sodium to flow into the dendrite, causing it to depolarize, sending it on its way to potentially cause another action potential. So that is really tying all of this together. You really have to be comfortable with the sodium, potassium ions moving, with the anatomy of the neuron, where this graded potential is occurring versus the action potential, and that graph. So hopefully that cleared up action potentials for you. If it did, be sure to hit that like and subscribe button so that you're notified when I upload other anatomy videos.